Hello, I'm Tyler Hayes from the Rochester Institute of Technology. Today, I am pleased to present our work, Online Continual Learning for Embedded Devices. A preprint of our work is available on arXiv, and our code is available on GitHub. Let's start off by defining what an embedded device is. It is a device that is purpose-built for a particular application. Due to hardware constraints, these devices are typically resource-constrained in terms of their amount of compute, storage, and power. On the other hand, online continual learning is the ability to update a learner one sample at a time on an evolving data stream. This closely resembles how humans and animals learn from data that constantly evolves in the natural world. Due to this evolving nature, data often has temporal correlations and inputs cannot be assumed to be independent and identically distributed, or IID. However, continually updating learners on evolving data streams comes with two major challenges. The first is that parametric models like neural networks suffer from catastrophic forgetting of previous knowledge when updated on non-IID data streams. This means that learners will forget previous knowledge in favor of new information. The second challenge is how to best enable backward and forward knowledge transfer to learn data better and more efficiently. Given these challenges, why should we study embedded continual learning? Since the natural world is constantly evolving, it is beneficial to immediately update a learner on new data so that it can make real-time updates and inferences. Moreover, by studying embedded continual learning, we can focus on designing agents that use less compute, which can enable on-device learning, which comes with several advantages. First, it means that updates and inferences do not need to be performed in the cloud, which could reduce privacy concerns and allow our agents to operate in possibly internet-deprived locations. It could also provide users with customized experiences without the need to process their data externally. Finally, studying embedded continual learning can facilitate several new applications such as customized smart toys, robots that travel around and learn about their environment, or AR/VR applications that can provide a user with a customized experience in their own home. Specifically, we argue that embedded supervised learning should meet the following criteria. First, online learning and inference must occur in a compute and memory-constrained environment. These constraints would often be defined by the embedded hardware that is specific to a particular application. Second, the agent must have the ability to learn from data presented in any order without catastrophic forgetting. This is because an agent often does not have control over the order in which data is presented, and it must be capable of performing well when the data is IID or non-IID. Third, the agent cannot assume that task labels will be available during inference, since this requires additional annotation efforts from humans, which might not always be available in the real world. Finally, the agent must be capable of efficiently learning and generalizing from as few labeled examples as possible. This encourages the agent to learn a robust world model while minimizing the number of annotations it requires from a human or oracle. This leads me to the goals of our study. Since embedded learning poses unique challenges to continual learners, we wanted to perform a comprehensive study to understand how well online continual learners perform when paired with CNNs designed for mobile applications. Specifically, we wanted to study the influence of 5 relevant factors for embedded continual learning on agents. This includes their ability to scale to large-scale, high-dimensional data, their ability to perform well in the presence of dataset imbalance, their ability to learn from temporally correlated video streams, their ability to perform well in low-shot learning settings, and their ability to perform well under memory and compute constraints. To study this, we first pre-trained several mobile CNNs on the ImageNet 1K dataset using supervised learning. We then studied the ability of 7 different online continual learning methods to update the output layer of the CNN to perform supervised classification. Specifically, we studied the following online continual learning methods: a simple fine-tuning baseline that does not have any mechanisms to mitigate catastrophic forgetting, the online multi-class perceptron algorithm, a streaming one-verse-rest classifier that compares a sample's distance to the nearest class mean and all other class means, the nearest class mean classifier, a Gaussian naive Bayes classifier that assumes feature independence and stores one running mean vector and one running variance vector per class, the streaming linear discriminant analysis classifier that stores one running mean vector per class and a shared class covariance matrix, and a replay model that stores either 2 exemplars or 20 exemplars per class. We chose 5 different CNN backbone architectures, 2 versions of the MobileNet v3 architecture, 2 versions of the EfficientNet architecture, and the ResNet 18 architecture, which is commonly used in continual learning literature. To evaluate the performance of each method, we report final accuracy as well as a variant of the net score metric. The net score of a method is useful since it scores methods across 3 different axes, namely classification efficacy, the amount of memory used, and the amount of compute needed. Specifically, A of M measures the final accuracy of the model, P of M is the total number of parameters required to store the model and backbone, C of M is the number of minutes required to run the experiment, and alpha, beta, and gamma are hyperparameters that tune the influence of each metric on the overall net score. We evaluate the performance of each method on 3 different datasets and data orderings. The Open Loris dataset consists of videos of 40 different object classes that were collected using a robot. For each class, there are between 1 and 9 videos of specific object instances that were collected under 4 different domains of varied difficulties. Examples of these different domains and difficulties can be viewed in the image on the right. To study the robustness of methods to different data orderings, we study an instance and low-shot instance ordering. The instance ordering shows the agent videos of each of the 121 object instances in a random order and evaluates the learner's performance on the full test set. In the low-shot instance setting, the learner only receives a single video of a single object instance from each class in the dataset, and it must generalize to unseen instances and domains in the full test set. This ordering is more difficult than instance, but mimics the real-world scenario where an agent would be subject to out-of-domain generalization. More details about these specific data orderings can be found in our paper. In addition to Open Loris, we also evaluate performance on 2 variants of the Places 365 dataset. Places 365 is a scene classification dataset consisting of 365 classes and over 1.8 million images. We use the full version of the dataset to evaluate the ability of models to scale, and we use a long-tailed version of the dataset to evaluate the robustness of learners to imbalanced datasets. For both versions of the dataset, we study 2 data orderings. The IID ordering randomly shuffles all of the images in the dataset and should be the easiest for models. The class IID ordering first organizes data by class and then shuffles images within each class. This is a non-IID ordering and should indicate how robust models are to catastrophic forgetting. Next, we will look at a subset of the experimental results from our paper. First, we wanted to understand how well each method generalized to out-of-domain inputs from very few training instances. We studied this by comparing performance on the Open Loris dataset using the instance and low-shot instance orderings. Note that both orderings use the full test set, so results across orderings can be directly compared. We averaged the performance of each method across all 5 backbone CNNs. It is interesting to first look at methods that performed well on the instance ordering but performed poorly on the low-shot instance ordering. This includes the perceptron and fine-tune classifiers, which likely have poor performance due to their inability to generalize to out-of-domain inputs. On the other hand, the nearest class mean classifier had strong performance on the low-shot instance ordering, but weaker performance on the instance ordering. Overall, the replay and SLDA classifiers had the best performance across orderings. Next, we wanted to understand how the CNN architecture choice affected performance on the Open Loris dataset. On the left, I'm showing the mean performance for each CNN architecture averaged across all continual learners. Overall, we say that the efficient nets yielded the best performance and ResNet 18 yielded the worst performance. This is interesting as ResNet 18 is currently the standard in continual learning literature, but yields worse performance and requires more memory and compute. On the right, I'm showing the performance of each continual learner using the EfficientNet B1 and ResNet 18 backbones. It is interesting to note that the architecture choice can have a large impact on some methods such as naive Bayes, which assumes feature independence. On the other hand, methods like SLDA and replay are more robust to architecture choice and only see a minor performance difference between the 2 architectures. Next, we wanted to study how robust each method was to scale and imbalance using the Places 365 and Places long-tail datasets respectively. Here I am showing the harmonic mean of each method across the IID and class IID data orderings, which emphasizes the importance of performing well on both orderings. Overall, we can see that SLDA, replay, and the nearest class mean classifier perform the best across both datasets. As expected, learning from the long-tailed dataset yielded worse performance for nearly all methods, demonstrating the difficulty of learning in the presence of imbalance. Learning from imbalanced data streams is important as the natural world is highly imbalanced. Finally, we wanted to summarize the performance of each continual learner across each of the factors evaluated. To do this, we normalized 5 scores to fall in the range of 0 to 1, namely a learner's net score, its ability to learn from temporally correlated videos, its ability to learn in low-shot settings, its ability to scale, and its ability to learn from imbalanced data streams. We plot these results on a radar chart where those methods with more area in their respective polygons performed better overall. These plots demonstrate that SLDA and replay performed the best overall, and the nearest class mean classifier performed well using fewer resources. We also found that using an efficient net backbone yielded the best performance across learners. Our work provides several avenues for future research. First, we performed a supervised pre-training phase on the ImageNet 1K dataset for the backbone CNNs. In the future, it could be interesting to explore the use of self-supervised pre-training. The challenge with this is that self-supervised learning does not currently work well for mobile CNNs. It could also be interesting to study additional pre-training datasets outside of ImageNet 1K. Beyond this, we used features from the penultimate layer of the mobile CNNs. It could also be interesting to study the use of features from multiple layers of the network and how to best combine them. An alternative research direction can consist of using continual learning methods that update feature representations. The challenge with this approach is that updating features requires more compute time and could lead to concept drift. Finally, more techniques to improve low-shot learning could be explored in addition to studying additional tasks and efficiency improvements. With that, I'd like to thank my advisor and co-author Chris Kanan for his support during the project. I'd also like to thank the NSF for funding our research. To summarize, we established the criteria needed to perform embedded continual learning. We then compared 7 online continual learners and 5 mobile CNNs across 3 different datasets and data orderings. We found that the SLDA, replay, and nearest class mean classifiers yielded the best performance. We also found that the efficient net architecture provided features that yielded the best performance across experiments. Thank you for your attention. If you have any questions, please feel free to reach out to me via email.